Okay, so I'm going to walk through the third free response questions practice. In the first set of problems, you have a set of data points that belong to an L function, which models the rate at which cars are leaving a garage. They also give you a function there, E, which is the rate at which cars are entering the parking lot. Time 0 represents 5 a.m. and the function has a domain of 0 to 12, so it would run 5 a.m. to 5 p.m. The first question is, what is the rate of change of E at time 7? So that simply is the derivative with respect to time of E of t, which is that big long function there, at time equals 7. So you literally load that E of t function into the calculator, have it come up with the derivative at time 7, and that comes out at 6.164. Now, the E of t is already cars per hour, so this is cars per hour, so it's going to be cars per hour squared. Part B asks how many cars enter the parking lot from time 0 to time 12, so this is an accumulation problem. So you take from 0 to 12 of the entering function, dt, which if you throw that in the calculator, you get about 520.070. They ask that to the nearest whole number, so that's 520 cars. Part C says use the trapezoidal rule to find 2 to 12 of L. So if you go from 2 to 12 of L of t and you're using the trapezoidal rule, okay, so for 2, so for the gap between 2 and 5, the two heights are 15 and 40. And we divide that by 2, and the width from 2 to 5 is 3. Then you take 40 and 24, and divide that by 2, and the width between 5 and 9 is 4. You're going to take 24 and 68, and divide that by 2, and the gap between 9 and 11 is 2. And then you take 68 and 18, divide that by 2, and the gap there is 1. This comes out to be 82.5 plus 128 plus 29 plus 43, which is a grand total of 345.4, which means that there are approximately 345.4 cars leave garage between time 2, which is 7 o'clock a.m., and times 12, which is 5 o'clock p.m. All right, so let's look at part D of this problem. Okay, so part D is going to give you total revenue. It's telling you that you have $5 coming in from time 0 to 6, $8 per car from time 6 to 12, and what's the total revenue to the nearest dollar? So you're taking $5 from 0 to 6 of E of t dt, plus $8 from 6 to 12 of E of t dt, which when you throw that in the calculator comes out as approximately 35.30 and some change. So the nearest possible dollar would be 35.30. All right, so that's the first problem. Okay, in the second problem, in part A, we're working with this weird piecewise function that has the break at 0. It asks for the average rate of change from -3 to 4. So average rate of change here is going to be f of 4 minus f of -3 over 4 minus a -3. So you need f of 4. f of 4 is -4 plus 3 times the cosine of 4 pi over 2. So that's -4 plus, that's 3 times the cosine of pi over 2, or of 2 pi, so that's just going to be 3. It's going to make that -1. I need the f of -3, which is going to be the square root of 9 minus -3 squared, which works out to be 0. So this is -1 minus 0 over, oh, she's coming to get a ladder, I think. Alright, so this is -1 over 7. So that's part A of the problem. Let's take a look at part B. So part B says find the equation of the line tangent to the graph at x equals 3. So first thing we need is the f of 3. The f of 3 here is going to be -3 plus the cosine, that's going to be of 3 pi over 2. So this is -3 plus 0, which is just -3. And then we need to take the derivative of f, but we need to take the derivative of f when I'm near 3. So that's on the second part of the part piecewise. So the derivative there becomes -1 times 3 pi over 2 times the sine, right? Sine of pi x over 2. So the derivative at 3 is going to be -1 minus 3 pi over 2 times the sine of 3 pi over 2, which is -1 minus 3 pi over 2, which is like 3 pi minus 2. Oh, sorry. Sine at 3 pi over 2 is that's positive, right? So it's 3 pi minus 2 over 2. So y minus y null is equal to m times x minus x null. So it's y plus 3, that's this one. The m is 3 pi minus 2 over 2 times x minus 3, that's the x value. It's probably a good idea to put the y by itself. Alright, and that's the answer to part B. Alright, so let's look at part C of the problem. Part C of the problem is now an average value. So this is 1 over 4 minus negative 3. Right, so it's 4 minus -3 integral, right, of -3 to 4 of f of x dx. So you have to break that apart. So this is going to be a 7th times -3 to 0. You follow the square root of 9 minus x squared dx. And then from 0 to 4, you follow the -x plus 3 times cosine pi x over 2 dx. I just threw that in the calculator to kind of make my life a little easier, and that came out as -0.133. Alright, so in our reality where everything's calculator active, that's not so bad of a problem. We need to look at the fourth part here. This is a little bit more theoretical, so let's look at part D. Alright, so you have to kind of think with the problem a little bit here. It's like asking you to justify whether or not this thing has an absolute maximum. It's going to have an absolute maximum if it meets the criteria of the extreme value theorem. Because you have a closed interval, so all you have to do is show continuity here. That's the thing that we don't know. And the way we can get, the only possible point of discontinuity is at 0, so we check the two limits. We take the limit as x approaches 0 from the negative side of f of x, and that's going to be the square root of 9 minus 0, which is 3. And then we check the limit as x approaches 0 from the positive side of f of x, And that's going to be negative 0 plus 3 times the cosine of 0, which this is 0, this is 3, so that's going to be 3. So this implies that f is continuous on negative 3, 4, which means by the extreme value theorem, f attains absolute max on that interval. All right, so that's all of number 2. Let's move on to number 3. All right, looking at number 3, here you've got that integral function, right? The g of integral, where the g is integral of f and some sort of graph there, right? So we need g of 0. So part A, you need g of 0, which is going to be the integral from negative 4 to 0 of f of t dt. From negative 4 to negative 1 is a triangle with a base of 3 and a height of 3. And then that little loop there is A. We know that that has an area of 3 from the problem. So we're going to subtract 3 from that. So this is 9 halves minus 6 halves, which is 3 halves. Okay. So we also need g of 4. Well, that's going to go from negative 4 to 4 of f of t dt. We already know from negative 4 to 0 is 3 halves. We just figured that out. We know that the big loop b is 5, so we're going to add that in. And then we need the integral from 1 to 4. And we know that that other loop is the function negative x squared plus 5x minus 4 dx. If I load this into a calculator, I get 11. So that's g of 0 and g of 4. Let's look at part B of the problem. All right, so this asks what is the absolute minimum value of g on this closed interval. It's not too hard to see. The absolute min will be 0 because at negative 4, that integral is 0. Okay, so to the right of negative 4, this thing's increasing, and then it decreases at negative 1 to 0. But note that decrease stays positive, right? Because remember, so g of 0 here is the only candidate for a local min. And the reason why it's the only candidate is it's the only one that is decreasing to the left of it, right? Everything else in the graph is positive. So g of 0 is the local candidate. But we know from above that g of 0 is 3 halves. And 3 halves is bigger than 0. So g of 0 is equal to that. And this is equal to f of negative 4. So that one must be local. Or not local, but absolute max on the interval. Not max. Whoops. Got a little carried away there. Absolute minimum on the interval. All right, so let's look at part C of the problem. When am I concave down? All right, so let's think about this. G prime of x, by the fundamental theorem of calculus, has to be f of x. G double prime of x is the derivative of f. So if the derivative of f, we want to know when this is less than 0. This means that f is decreasing. So the second derivative of g will be less than 0 when f is decreasing. So g is concave down on, well, where is f decreasing? It's decreasing from negative 2 to negative 1/2. It's decreasing again from 1/2 to 1. And then it's decreasing from 5 halves out 2, 4. So these are the three intervals where f is decreasing and g is concave down. All right, so that's problem number 3. So let's take a look at problem number 4. All right, so problem 4 gives us this ellipse. It tells me that 4x squared plus 3y squared plus 6y is 9, and it wants dy dx. It wants to verify that dy dx is negative 4x over 3 times y plus 1. This is just implicit differentiation. This is going to give me 8x plus 6y dy dx plus 6 dy dx is 0. So you can pull the 6y plus 6 dy dx out and bring the negative 8x to the side. Dy dx is going to be negative 8x, and we can pull a 6 out of this, y plus 1, and then just factor out the 2. It's going to be negative 4x over 3 y plus 1. All right, so that's part A of the problem. Just do the implicit differentiation and kind of follow your nose. All right, so part B asks for the second derivative. This is not so bad either. Start with what you ended with on the first part. So you have that dy dx is negative 4x times 3 times y plus 1. So you have to use your quotient rule here, right? d2y dx squared. So it's low d high minus high d low dy dx, because it's implicit, over low squared. The only thing that I have to do in order to get this in terms of x and y, I can clean it up a bit. So it's this negative 12y minus 12 plus 12x times, and the dy dx is negative 4x over 3 times y plus 1, all over 9 times y plus 1 squared. Now I have the second derivative in terms of x and y. I can stop there. I don't have to do any more simplifying. I'm good. That problem is done. All right, so let's move on to number 5 here. All right, number 5 gives me a series. So we have the sum from n equals 1 to infinity. And then it asks me in part A to put the p as 3 and the x as 8. So that's not going to change the alternator here. If I made x 8, 8 minus 3 gives me 5 to the n. And then I have a 5 to the n down here, and now I have an n to the third. Those cancel, gives me the sum n equals 1 to infinity of negative 1 n plus 1 over n to the third. Now this clearly converges by the alternating series test, but it wants to know if I converge absolutely. So I take the absolute value of that, which just gives me, which is a p series where p is greater than 3. So this converges, which means the series converges absolutely. All right, so the big trick here is that's not the case with part B. Right, so let's look at part B. They play the same game, but this time they make p 1 and they leave x as 8. So n equals 1 to infinity. The alternator doesn't change. X is 8, leaves this as 5 to the n. This stays as 5 to the n, but then I just get n here. Okay, so I think you could see what's going to happen here. I get n equals 1 to infinity, negative 1 to the n plus 1 over n. That converges by alternating series test. However, when I take the absolute value, I get 1 over n, which diverges, it's harmonic. So this one converges conditionally, right? This is not an absolute convergence because the series of the absolute value does not converge. All right, so let's look at part C of the problem. All right, so part C mixes things up a little bit. It says when x is -2, does the P series converge, right? So let's see what happens when I just throw the x is -2 in here, right? So this is n equals 1 to infinity. I get -1 to the n plus 1. -2 is going to make this -5 to the n over 5 to the n to the p. All right, so that's going to give me -1 to the n plus 1 times -1 to the n over n to the p. Right, so this is n equals 1 to infinity. And that's just going to be -1 up top because that's 2n plus 1 over n to the p. So this is negative n equals 1 to infinity 1 over n to the p. So this is going to converge when p is greater than 1. This is a p series. All right, so that's the whole deal for that one. Let's look at part D. All right, I can almost guarantee you there will be an alternating series error-bound question on here, because the thing is that Lagrange error bounding is out because that's in Taylor and Maclaurin. However, the alternating series error bounding is still in because all you need is an alternating series for that. So they're making P1, they're making X 3.1. So we get n equals 1 to infinity, -1 to the n plus 1. That's going to give me 0.1 to the n over 5 to the n, and then p is 1, so that's just going to be n there. All right, so I rewrote this just to make some sense of it for myself. I have an alternator. This is going to be 1 over 50 to the n times 1 over n. All right, this converges by AST. That's pretty clear. All right, so let's see what goes on here. If I take this and estimate this with the first two terms. All right, so when n is 1, this is positive. This is just going to be 1 over 50, and that's going to be 1 over 1. The second term, don't put the plus sign there. The second term is going to be negative. So this is going to be 1 over 50 squared, so that's 1 over 2500 times 1 over 2. So this is 1 over, actually, let's see, that's 1 over 50, so that is 100 over 5,000 minus 1 over 5,000. Makes my estimate here 99 over 5,000. Now, we want to show that that is within 1/300,000ths. So the error here has to be bound by the next term, which would be the third term, which is 1 over 50 to the third times 1/3, which, let's see, that's going to be 1 over 125,000 times 1/3, which is 1 over 375,000, which is clearly less than 1 over 300,000. So there you go. We have verified it by using the alternating series error bound. We just used the third term when we estimated using the first two. All right, so there you go. If you've got questions, do the drop-in, do some emailing, get some help. But there's a third problem set for you.